In this video, we're going to look at two basic rules of probability. We're going to use a multiplication rule to calculate probabilities. We're going to use the addition rule to calculate probabilities, and we're going to use combinations to calculate probabilities. So we're actually going to start with probability and combination. So we are going to look at when we have importance of order, when we pick our pieces of data, and when we don't care about order. So a combination is an arrangement of objects in which no particular order, so that doesn't matter the order. Whether you've flipped a head first and then a tail, it doesn't matter if you've flipped a tail first then a head. You just got a combination of a head and a tail. The order in which you got them doesn't matter. If the order does matter, then it's a permutation. The way in which we're going to find the combination of the total combinations that you're going to have is this. It is the combination of n choose r. You might also see this also on your calculators. You might have the n choose r button. So n is the number of pieces of data you have, and r is what you're going to choose. So as an example, if you have 10 pieces of data and you're only going to choose 5, then it would be 10 choose 5, and you would do 10 factorial because that's the number of pieces of data you have. And then in the denominator, it is 10 minus 5 factorial multiplied by 5 factorial. And what is factorial? Well, the n with this exclamation mark, the n with the exclamation mark is read as n factorial, which means all the numbers from 1 to that number n is going to be multiplied together. So as an example, we have the 5 factorial. 5 factorial means 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. That's what factorial reads. And 0 factorial is always 1. That's just the definition. Accept it. So let's take a look at an example in which we have a combination. You're going to pick you have a pick 4 lottery. It has 4 digits in no specific order. The digits are between 0 and 9. How many different combinations are there if one digit may be used more than once? If you are using your calculator, you would use the 10 choose 4 button. If you're not using your calculator, then you would use this formula here, which is 10 factorial over 4 factorial multiplied by 6 factorial. And that's because this is 10 minus 4 factorial. That is this part of the formula. And then you would do the factorial button on your calculator, and you would end up with 210. Now, let's bring this into probability. A pick 4 lottery has 4 digits of no specific order. The digits are between 0 and 9. What is the probability of choosing the correct digits? Well, first of all, we're going to tell you what the event is. The event, or E, whatever you want to label it, E for event is fine, is to pick the correct digits. So the probability of picking one correct combination would be 1 out of the total sample space, which is 210. In this case, the probability of winning a pick 4 lottery is 0.000476. So approximately 0.5% chance of winning a pick 4 lottery that has 4 digits where there's no specific order. If order matters, then it's a permutation. So this is a permutation of n pieces of data, and you want to fill r number of slots. Notice this is going to be n factorial over n minus r factorial, which means my sample space is considerably larger. And that's because if you have a sample space where you get a head or then a tail, if it's a combination, then this is the same thing as a tail then a head. So that's why the sample space for a combination for this example would only be 1. But if you have a head then a tail, that is not going to be the same thing as a tail then a head for a permutation. Because the one that you pick first, the order matters. So your permutation sample size becomes much larger. When you're doing permutations, you can be thought of as n minus 1, n minus 2, all the way down to n r minus 1. So let's do this example by looking at what this look like with this formula to find a code that has 4 digits in a specific order. And the digits are between 0 and 9. How many different permutations are there? Because, you know, with a code, order matters. So in this example, we would have P, and I would have 10 choose 4. And you're like, why 10? Well, because if you count 0 as being a number all the way up to 9, there's 10 possible numbers from 0 to 9. So this would be 10 factorial over 10 minus 4 factorial. And what you could do in your calculator is you could write this as 10 times 9 times 8 times 7. Don't forget the 7. I wanted to just jump to 6. Times 7 times 6 factorial. And then in the denominator form, 10 minus 4 is 6 factorial. So I could get down to just 6 factorial. And those two numbers would cancel. And so what I have is 5,040. Now, what is the probability of picking the correct code if you have 4 digits and the digits are between 0 and 9 and order matters? Well, again, E is going to be picking the correct code. Picking the correct code. So the probability of this event E happening is going to be 1 out of 5,040, which is going to be 0.0002. So in other words, you have 0.02% chance of getting the correct code. So that's where permutations and combinations come into play with probability. Let's talk about the multiplication rule. So if we recall from the fact that the probability of A given B is equal to the probability of the intersection of A and B, so A and B is A intersect with B. Just as a reminder, we can write this as the probability of A intersect B. So in other words, that overlap only, divided by the probability of B. If A and B are two events defined in a sample space, then just doing some basic algebra that A, or probability of A intersect B, is going to be the probability of B multiplied by the probability of A given B. If A and B are independent, then we know from before the probability of A happening given B is just the probability of A happening. So, if the probability of A intersect B is equal to the probability of A given B multiplied by probability of B, then A intersect B just becomes the probability of these two multiplied together. The probability of A happening multiplied by the probability of B happening. Consider Becky's deck of cards and Bucky's deck of cards and his friend Satchel. What is the probability of Satchel drawing a heart without replacement and then a spade? So let's define what we have. So H is drawing a heart. Drawing a heart. A heart. And S is drawing a spade. So the probability of drawing a heart first is there are 13 hearts in a deck of cards of 52. So 13 divided by 52. Now, what is the probability of drawing a spade and you did not replace that card? Well, there's only 51 cards now, but there are still 13 spades. So the probability of drawing a heart without replacement and then a spade, in this case, would be the probability of E intersecting with S. They are not quite independent because of the fact that I have reduced the number of cards, but you drawing a heart does not affect you drawing a spade, and vice versa necessarily, because you haven't reduced the number of hearts or the number of spades in the deck. You just reduce the number of cards. So this can be done as a probability of the heart first and then multiplied by the probability of the spade. And so this is going to be 13 over 52 multiplied by 13 over 51, which gives us a 0.0637, or in other words, 6.3% chance of drawing a heart first and then a spade. Here's another example. Inside a box of every cereal box contains a surprise gift. The store manager assures employees that 14 of the 65 boxes on the shelf have a secret decoder ring inside, and the other 51 boxes on the shelf contain a different gift. If 2 cereal boxes are randomly selected from the shelf to purchase, what is the probability that both of them have the secret decoder ring? Okay, so this one I'm going to do with combinations. So if E equals the decoder ring box, and this is a combination, so I have to figure out what my sample space is. Well, in this case, it is 65, choose 1, which if you use the formula up above or use your calculator, you're just going to get 65. So then the second time, you're going to have one less box, so that's going to be 64, choose 1, which in this case equals 64. So these are the sample space sizes. Let's call E2 as the decoder ring on the second attempt. So what we're asked to find is the probability of E intersect E2, which I'm going to have for the first go around, it's going to be the probability of getting 14 out of 65 boxes. The second go around, I'm going to have one less box of the decoder rings, and I'm going to have one less box total. So I end up with an answer of 0.04375. So in other words, I have 4.4% chance of choosing 2 boxes with a decoder ring, which really is not that great of a chance. Now let's talk about the addition rule. If A and B are defined as a sample space, then A or B, so A union B, just want to give you that notation, is equal to the probability of A happening plus the probability of B happening minus the intersection of A and B happening. If the A and B are mutually exclusive, then the intersection or the AND statement is 0. If probability of A or B is equal to this, then if they're mutually exclusive, then the probability of A union B is just the probability of A happening and then the probability of B happening and added together. Bucky has a deck of cards, again 52. He wants his friend Satchel to draw a card. After Satchel draws a card, he puts it back in the deck. Find the probability of Satchel drawing a queen or a spade. So Q is drawing a queen. S is drawing a spade. So there is overlap. So the probability of a queen and a spade is 1 out of 52 because you have one spade that's a queen, or you have one queen that's a spade. So we don't have, these are not mutually exclusive, even though we have put the card back. So the probability of Q or S, the union of Q and S, is the probability of the queen happening plus the probability of picking a spade minus the probability of the intersection of Q and S. So in this case, the probability of getting a queen, there are 4 queens in the deck of 52 cards. There are 13 spades in the deck of 52 cards, and there is one out of 52 cards that is both the queen and a spade, that's their intersection. So the answer for this one is just going to simply be 16 out of 52, 14 plus 13 minus 1, or it's 0.3077. So in other words, we have a 30.8% chance of picking a queen or a spade. Now suppose we have a special 29-sided die and it's rolled once where every face is marked for the number between 0 and 39. And let's assume it's a fair die. What is the probability that the die will land on a 3 or a 15? So we ask ourselves, is these mutually exclusive? And the answer is yes. Rolling a 3 or a 15, there is no overlap. So in this case, I'll say E is rolling a 3. B is rolling a 15. So then B, the probability of E intersecting with B is 0. So the probability of E union B is just going to be 1 out of 29 plus 1 out of 29, which is 2 out of 29, which is 0.069. So in other words, you have about a 7% chance, of rolling a 3 or a 29. Let's take a look at this last example here. A student goes to the library. Let event B equal the student checks out a book. Let D equal the student checks out a DVD. Suppose that the probability of checking out a book is 0.4, the probability of checking out a DVD is 0.3, and the probability of checking out a DVD, given that B has already happened, is 0.5. Are B and D independent? And the answer is no, because this conditional probability is not equal to 0. So then what I want to find then is I want to find the probability of B and D. Well, we know from up above, this is going to be the probability of D given B multiplied by the probability of B, which is going to be equal to 0.5 multiplied by 0.4, which gives me 0.2. That means I can now do the B or D. So the probability of B or D is the probability of B happening plus the probability of D happening minus the intersection of B intersect with D, or in other words with the AND symbol. So this is going to be 0.4 plus 0.3 minus 0.2, which gives me 0.5. In other words, about a 50% chance of them picking up a book or a DVD. And that's it for this video.